managing energy. This is only a fraction of the total picture confronting the automotive engineers. For if all these engineers who designed Chevrolet cars and trucks had to be concerned about was applying the engine's power in a straight line, their task would be a lot simpler. But in the driving environment, you don't always go straight. You have to maneuver quickly and precisely. And that requires handling, or more accurately, directional control. The most crucial factor in directional control is the tires. In fact, the role of the tire is so important that suspensions are often designed around it. Now, one of the most sophisticated handling cars ever built, the Corvette, was designed in just this way, from the tire up. The challenge of tire design is that it must often embody what seems to be conflicting performance characteristics. It must have strength to resist damage, and yet still be pliable enough to cushion impacts. It should have a smooth surface for maximum contact on dry road, and a pronounced tread pattern for handling in wet weather. And it should be soft for good traction and hard for durability. So every tire design is really a combination of these needs. Dramatic advances in tire technology have been achieved in recent years to develop the best possible all-around tire. There are two basic designs, bias ply and radial tires. Bias ply tires usually have from 2 to 8 plies. The ply is a layer of rubber-coated fabric. The layers are made up of cords that cross at an angle, or bias. This angle affects riding comfort and steering accuracy. The larger the angle, the greater the riding comfort. The smaller the angle, the better steering accuracy. To strike a balance between these characteristics, most bias ply tires have angles somewhere between both extremes. Radial tires represent a breakthrough in tire technology. Instead of crisscross patterns in the plies, radials have parallel plies that radiate from one side to the other, crossing the center of the tire. This design offers a flexible sidewall for a soft ride, but only limited directional control. This problem is solved by crisscrossing fabric or steel belts around the tire, which results in better handling characteristics. The benefits of the radial ply tire include greater cornering capability because the flexible sidewall allows the tread to stick to the road and not skid. And because the belts reduce the distortion of the tread, handling capabilities and tread life are increased. Radials also offer a significant increase in fuel economy over bias ply tires. Less rolling resistance from radials can mean a 5 to 7% improvement in fuel economy. Tires are not only a key factor in any vehicle's handling characteristics, but they also provide a primary line of defense against road shocks. But even so, if the tires were connected directly to the vehicle, it would be uncontrollable and literally shaken apart as it was driven down the road. What we must have is a suspension system to keep the wheels in contact with the road, smooth out the bumps, provide the necessary directional control during acceleration, braking, and cornering, and support the weight of the vehicle and its cargo. Suspension and handling engineers strive to design the suspension so that it supports as much of the vehicle's weight as possible. The more weight that's suspended, the less shock that's transmitted to the passengers, and the greater ability of the vehicle to maintain control. In designing suspension systems, the ideal spring would be one that absorbs shocks rapidly and returns to its normal position slowly. A single spring by itself cannot perform both functions in a vehicle. The solution is to use a spring that absorbs shocks rapidly and combine it with a shock absorber, which slowly returns the spring to its normal position. The shock absorbers used on vehicles are similar in construction to a familiar door closer that you probably have on your screen door to keep it from slamming. So as you see, the shock absorbers are really misnamed. They only limit or slow down the spring's return. The springs do the actual job of absorbing road shock. The springs and shock absorbers can be arranged in several configurations. One of these is an independent front suspension, where each wheel is attached separately to the frame by an upper and lower control arm. The spring and shock are mounted between the arms. Now, this arrangement allows an independent wheel movement up and down so that both tires retain better contact with the road and a more level ride. A variation of this suspension is the McPherson strut. It combines the coil spring and shock absorbers into one unit. The coil spring is attached around the upper half of the strut, and a shock absorber is mounted inside. The result is more efficient packaging of the front suspension components and reduced weight, which are important considerations in today's smaller, lighter Chevrolets. But as effective as all these components are in suspending the weight of a vehicle and absorbing road shocks, there are other forces that must be dealt with. In a turn, for example, centrifugal or outward force is generated, causing the vehicle to lean. To counteract this tendency, a stabilizer bar is used. It runs across the vehicle from one side to the other, twisting as the vehicle leans. This resists that lean and helps to keep the car level. The stabilizer bar also helps keep the tire flat on the road during cornering. Modern designers continue to strive to create a vehicle designed to deal with all handling forces. This is the objective as they work toward the creation of that impossible dream, the perfect car and truck. Since the invention of the wheel, man has dealt with the problem of moving weight. Over the years, many types of vehicles have evolved to meet the requirements of various loads. Around the turn of the century, a country doctor may have ventured out and hitched his horse to a carriage similar to this. Now, this vehicle was obviously designed to carry passengers with as comfortable a ride as possible. In the 18th century, the term truck was first used to describe a wagon designed to carry weight. They used thick slabs of wood like this, reinforced with heavy iron. And the suspensions were designed for carrying weight, obviously not for comfortable transportation. The need to carry more weight, faster and more reliably, increased as the days of animal horsepower diminished and the cities grew. The novelty of the horseless carriage quickly transformed into the serious business of automobiles and trucks. Now, these developments coincided with technological advancements that provided more powerful engines and new suspension designs capable of carrying larger cargoes. The key to a vehicle's load carrying capacity is the assembly known as the chassis, which includes the frame, axles, suspension, wheels, and tires. The basic component of the chassis is the frame, the backbone of the vehicle. Some cars and light-duty trucks have an integral body and frame structure, while others have a separate frame to which the body is attached. A vehicle's load-carrying capacity can be no stronger than its frame. All chassis components are attached to it. The frame's strength is determined by two factors, design and materials. The design can be channel-shaped, box-sectioned, or a unitized body frame with various depths, widths, and thicknesses that can be incorporated to meet the load requirements. The strength of material used in the frame is expressed in a number of terms, such as yield strength, which provides a measure of the metal's ability to withstand load forces. Front and rear axles alike are rated by their load-carrying capacity. Now, this capacity is not determined solely on the strength of the axle, but rather as part of a system, including the axle springs, shock absorbers, tires, and wheels. There are three types of springs in common use: coil, leaf, and torsion bar. Coil springs are simply coiled steel rods that absorb shock by compressing and expanding. They are normally used on the front and rear suspension of passenger cars and on the front suspension of trucks. Leaf springs consist of steel leaves of varying lengths that are clamped together. The long, flexible leaves handle the weight of the vehicle when it's empty or lightly loaded. The short, stiffer leaves come into play when the vehicle is heavily loaded or the road is rough. Trucks usually employ leaf springs in the rear because they're effective for heavy loads. Torsion bar springs absorb shock by twisting. Many Chevrolet four-wheel drive trucks use torsion bar springs to cope with the rough conditions encountered in off-road driving. The final component of the chassis is the wheel tire combination. When we're talking weight capacities, the wheel is not rated specifically. Rather, it's matched with a tire chosen for its load-carrying ability. The tire's rating is designated by the term load range, usually imprinted on the tire. The load range is an indication of the tire's strength, represented by a letter, A or B, primarily for passenger cars, or C, D, or E, which are rated for heavier loads, such as those for trucks and trailers. The weight-carrying characteristics of a design are only half the story of weight management. Materials used in the design and construction of a vehicle also play an important role in helping to move cargo efficiently. Overcompensating with too much material, too much weight, can severely handicap a vehicle's ability to move cargo at a reasonable cost. And the high technology age has certainly helped the cause. The use of tough, lightweight alloys, plastics, fiberglass, and even ceramics help to reduce structural weight without necessarily reducing interior dimensions or cargo capacity. Well, for example, this monoleaf spring was designed to have the same weight-carrying characteristics as the old design, but weighs 33 pounds less. Plastics and lighter metals have played an important role in maintaining structural integrity while providing tough, lightweight designs. Interior trim and components, engine parts, even fuel tanks have been carefully studied and redesigned where feasible. The result is substantial weight reduction without sacrificing load capacity and stress tolerance. This translates into reduced power requirements, which in turn allow the use of smaller, more fuel-efficient engines. The fragile balance of load-carrying capability and efficiency has become more and more attainable. There are two ways of looking at weight management: the weight of passengers and cargo, which is the weight-carrying capability of the vehicle, and the weight of materials used to build the vehicle, incorporating designs and materials into a structure that will support the load without overcompensating. A perfect balance of weight and efficiency. It's not there yet, but they're working on it. Our increasing dependence on machines in our everyday life has created a whole new field of scientific endeavor called ergonomics, the study of the mutual adjustment of men and machines. In other words, how we as people relate to machines, and vice versa. In the case of motor vehicles, as we work to make them more fuel efficient, designing the space available for the driver and passengers becomes more and more of a challenge. In vehicle design, it's the human factor that ultimately defines the vehicles. Now, people requirements for space, visibility, control, entry, exit, comfort, and security determine everything, from where a radio knob will go to the total size of the vehicle. But before any of these kinds of details are determined, even more basic questions have to be answered. For example, is the vehicle primarily for passengers, cargo, or a combination of both? How many passengers? How much cargo? Off-road use or strictly a highway vehicle? What are the maximum and minimum heights of those expected to drive the vehicle? As these questions are resolved, the design begins to take shape. Chevrolet's objective is to optimize the man-machine relationship. In other words, The ergonomics must be right. The key is the human factor. Since we come in all sizes and shapes, from a 5'2" teenager to a professional basketball player reaching 7 feet or more, engineers need to determine the optimum placement of controls, seat adjustments, and lines of sight that will accommodate the vast majority of American drivers. To do that, engineers have precisely measured thousands of people using this machine called an anthropometer. It can provide them with a precise, accurate description of the physical makeup of the American driver. Using this data, engineers can ensure that interior features are usable by 95% of the population. That's the objective, 95%. This use of ergonomics and space-efficient design techniques has become increasingly important in recent years. The industry's commitment to fuel-efficient vehicles has had a tremendous impact on interior design, on space utilization. Now, one of the easiest ways to improve fuel efficiency is to reduce vehicle size and weight. A smaller car or truck burns less gas. Simple. But as vehicle size was reduced, engineers had to rethink the conventional front engine rear drive configuration that was the industry standard. In smaller cars, a front-wheel drive arrangement with the engine mounted crossways or transversely produces several advantages connected to space utilization. For example, to make room for the engine, upper control arms in the front suspension are eliminated. This allows for a lower hood line to reduce aerodynamic drag. The compact packaging of the engine, transmission, and drive components reduces their intrusion into the interior space. The transmission hump in the front compartment is smaller, and the drive shaft tunnel in the rear disappears. As vehicles grow smaller and lighter, unitized body frame construction is replacing full perimeter frames. This allows space formerly occupied by the frame to be used for passengers and cargo, at no sacrifice to the vehicle's structural integrity. While vehicles were shrinking on the outside, they still had to provide adequate passenger room. That meant redesigning all sorts of components, well, even window mechanisms, so that, in turn, the thickness of doors could be reduced, freeing up more interior space. This totally new approach to space utilization involves everything from the seemingly insignificant window mechanism to major reconfigurations of the engine and drivetrain package and design of the interior compartment. It's no wonder that today's vehicles are often referred to as being reinvented. What's next? Well, if history is any indicator, we'll continue to see an emphasis on fuel-efficient designs that put a premium on weight savings and better utilization of space. But, as has always been the case, it'll be the human need that makes the final determination of what tomorrow's vehicles will be. Concepts, ideas, dreams. This is how they come together. Whatever you call them, they're here. Translated into metal, fiberglass, and plastic. Referred to by exotic names such as Aerovet, Stingray XP87, Manta Ray. Vehicles of the future. From a perspective cast decades ago, a time when turbine power seemed like a viable alternative. But that was before emission standards were enacted. Some thought that rotary power was the answer for greater performance in a compact design. But that was before the emphasis on fuel efficiency. Government-mandated bumper height and impact standards conflicted with many designers' flowing lines. Does that negate the value of these concepts? Hardly. Because much of what we know today about the aerodynamic effects on vehicle design was learned during the development of these idea cars. The same is true of the lighter weight materials, alloys, and plastics used in our present-day vehicles. The benefits derived in fuel efficiency alone more than compensates for the investment made in these dream cars. You know, it's hard to believe that the technology reflected in this design is more than 2 decades old. But much of what was experimental then is now commonplace. Well, disc brakes, for example, were a rarity in the mid-'60s, and the opposite is true today. So what does the technology of today portend for the future? In a word, excitement. The Aero 2002 concept car, a 4-passenger experimental subcompact. This vehicle features front-wheel drive and an aerodynamic shape with a coefficient of drag of 0.230. Among the advances incorporated into the 2002 is a 4-point air suspension system that lowers the vehicle closer to the ground during high-speed driving to enhance its aerodynamic qualities. Perhaps a feature we'll see on future production cars. A completely new and different type of vehicle is the lean machine. It takes its name from a slender silhouette and the capability to lean into a turn. It can also travel up to 200 miles on a gallon of gasoline. Somewhere between the Aero 2002 and the lean machine is the TPC, or 2-passenger commuter, a vehicle that delivers up to 95 miles per gallon highway and 68 in the city. Its small size and maneuverability make it an ideal urban car. Does the future offer anything more than aerodynamics and fuel efficiency? Remember, the key word is excitement. Dreams, ideas, concepts. This is how they all come together, where the ingenuity of man deals with the laws of nature and bends them to his will to produce a mobile society, people in motion. What lies ahead? Well, it's hard to say, but when it comes, I sure want to be behind the wheel.